So now that we know how to calculate the factor of safety with the Psi-Wu criterion, let's look at an example. So here was our calculation of the factor of safety. So these terms A and B, just solving a quadratic equation based on the strength numbers and the given stresses. And so let's look at an angle ply laminate. It's going to be symmetric, and the one on the left is made of plus and minus 30 carbon epoxy layers with total thickness of 1/10 of an inch. The one on the right has only plus 30 layers, so it's not balanced. It's still symmetric and also has a thickness of 1/10 of an inch. And both of them are going to be subjected to an axial stress resultant of 1,000 pounds per inch. So here are the mechanical properties we're going to use for carbon epoxy. Again, they're the ones that come out of the summary pages of the course pack. And so we can calculate the stresses with your spreadsheet, since both of these are symmetric. And so for the plus 30 laminate, here are the stresses. Now these are for the plus 30 layers. The minus 30 layers will be the same except for the sign of the shear stress. If we look at only the plus 30 laminate, there are the stresses. And one thing that's kind of interesting to see here is that the 7,500 psi sigma 1 is actually quite a bit less than the sigma 1 of the plus and minus, that is the balanced laminate. However, sigma 2 and tau 1,2 have much higher magnitudes, and remember that the strength in the transverse direction and the shear directions are much lower than they are in the fiber direction. So we'll see how that plays out when we calculate the factor of safety. All right, so we have to calculate the strength parameters. And one thing to remember is that the compression strengths always go in as negative numbers. So for F1, we get this number, which ends up being negative because the tensile strength is greater than the compressive strength magnitude. F2, those are reversed, so it becomes a positive value because of the fact that the compressive strength magnitude is greater than the tensile strength magnitude in the transverse direction. Notice both of these have units of 1 over psi. They're going to get multiplied by the stress in psi, so that product will become non-dimensional. F11 minus 1 over xtxc. Again, xc goes in as a negative number, so it cancels out that negative. You end up with a positive value, a very small number. Notice the exponent times 10 to the minus 12, but it's going to get multiplied by, in this case, sigma 1 squared. So 1 over psi squared for the units here gets multiplied by psi squared, so again becomes non-dimensional the product. Similarly for F22 and for F66, which is 1 over the shear strength squared. All right, so for the plus 30, plus and minus 30 laminate, we plug in for the values of the parameter A with the strength values we just calculated and the stresses that we showed earlier, and there's our value for A. For B, using the linear terms, we come up with this value, and now we plug those into the equation for the factor of safety, and the number comes out to be 7.79. So we can increase the stresses by about a factor of 7.8 before failure is predicted. In fact, 7790 pounds per inch would be the predicted failure load. And if we want to check this real quick to see that we calculated the factor of safety correctly, if I just multiply all of the stresses by 7.79, in other words, analyze the laminate with an applied stress resultant of 7790 pounds per inch, then there are the stresses. If I now plug those stresses into the Psi-Wu polynomial and go through all the math there, I'll find out that the Psi-Wu polynomial does indeed equal exactly 1. So we are predicting that failure occurs when the stresses reach these values. One thing that's kind of interesting here, if you look at the magnitude of tau 1,2, and what you'll see is that the magnitude of that shear stress is actually greater than the shear strength. So it's very difficult to anticipate all of the interactions that occur between the stresses. But in this case, what we're saying is that a transverse compression on the layer increases the shear strength. That doesn't seem to be unreasonable, but again, it does show you that there are some complex interactions between the stress states. So if I look at the equivalent strength of that laminate and just say, okay, it can take 90 pounds per inch, and it's only 1/10 of an inch thick, then that gives us an equivalent strength of 77,900 psi. That's calculating that will let you compare that to say, what would uh, a similar thickness of aluminum or steel strength be, and so let you make those comparisons. Now, if we look at the plus 30 laminate, without going through all of the calculations again, we find the factor of safety is much lower, only 2.01, and so we would say the strength in the x direction, 2.01 times the applied load divided by the total thickness of 1/10 of an inch. So equivalent strength then of only 20,100 psi in the axial direction. Now if we do this for other angles, you can see that the balanced plus and minus laminates are significantly stronger than the just a plus theta laminate by itself until we get out, of course, to the very high angles, or if we're at zero, where it doesn't matter. But one thing that's kind of interesting here is that for these balanced laminates with the strength parameters we put in between 0 and 10 degrees, the strength's actually predicted to be greater than the 300,000 psi of tensile strength of the 0-degree laminate. Again, kind of interesting. So as we say, the balanced laminate's not only stronger, but as we've seen before, the unbalanced plus theta laminates can also will also result in some coupling effects that most of the time you don't want. That is, you pull on it in the x direction, you really don't want it to shear one way or the other, so the balanced laminate doesn't do that. Now if we do kind of a similar argument where we put on instead of the applied load in the x direction, if we put on an applied shear load in of xy, we can look at the strengths of plus and minus laminates, in other words, their shear strength. And as we might expect, the plus and minus 45-degree laminate is the best for resisting in-plane shear stress. So we kind of did that earlier when we looked at a drive shaft example, but we did that before we had a failure criteria, so we just looked at that in terms of the maximum stress criterion. So in the next video, what we're going to do is go back to that drive shaft problem and again evaluate it with the psi-wu criterion in this case.